Hello, my name is Jeremy Boyd, and for this presentation, I will be talking about the NP-complete problem that I chose to do for my final project. I will also be talking about how I solved it, the test I ran, and their results. So the problem I chose for my project was the partition problem. Now, what is the partitioning problem? In computer science, the partition problem, also known as number partitioning, is the task of deciding whether a given set of positive integers can be partitioned into two subsets such that the sum of the numbers in the first subset equals the sum of the numbers in the second subset. The partition problem is NP-complete, but there are heuristics that solve the problem in many instances, whether it's either optimally or approximately. For this reason, it has been called the easiest hard problem. The approach I took to solve this problem was using a hybrid genetic algorithm with a wisdom of crowds approach. To start, I'm going to break down these two parts of my program and then show how I put them together in order to solve the partition problem. My program starts with the genetic algorithm, which is a meta-heuristic inspired by the process of natural selection, where the fittest individuals are selected for reproduction in order to produce offspring of the next generation. I'm going to briefly walk through how I developed my genetic algorithm to tackle the partitioning problem. Here is the function that acts as my genetic algorithm by taking in a set of numbers, the population size, the number of elite individuals that will be kept, the mutation rate, and the number of generations to be produced. The function starts by creating an initial population, which calls the partition function. A solution is represented by a binary string parallel to an array of the input members, such that each character in the binary string represents one number in the input array. Each number in the array is represented by the character in the binary string whose position in the string is the same as the number's index in the array. For each binary character in a candidate solution, if the character's value is 0, the corresponding number is a member of the first subset in the partition. Otherwise, the binary character's value is 1, and the number belongs to the second subset. This is how each generated individual is being partitioned. This picture shows what this process looks like. Here you can see 3 chromosomes and their corresponding partitions for the binary string encoding of set A. As you can see, if the corresponding number to the chromosome is in the left subset, it's a 1, and if it has a 0, it's in the right. Next, the genetic algorithm goes into a for loop that produces multiple generations based on my chosen value. The first step in this next generation function is to rank the individuals by giving them a fitness score. I did this by splitting the binary strings up into their 2 subsets and inputting them into my fitness class, which calculates the fitness score by calculating the sum of the first subset and then calculating the sum of the second subset. Then the fitness score is the absolute value of the difference between these two sums. A lower fitness score is better because that means the difference between the two sums was closer to 0, which is what I want. A dictionary is used to hold the index of a binary string in the population and its associated fitness score, and they are sorted by smallest to largest fitness score. Next, the mating pool is created by using fitness proportionate selection. Using this method, the fitness of each individual relative to the population is used to assign a probability of it being selected. This gives each individual a fitness-weighted probability of being chosen. This also includes a feature called elitism, which ensures that the best performing individuals from the population will automatically carry over to the next generation, ensuring that the most successful individuals persist. I then used a for loop to retrieve the elite partitions, which in my code is always 1/5 of the amount of numbers in the set. And then I used another for loop where a randomly generated number is compared to the weights of all the remaining partitions to determine if they will be included in the mating pool or not. Next, it's time to generate the children using two-point crossover. Two-point crossover is when two indices of the chromosome are chosen and each of the two parent chromosomes are cut at those indices. For me, the first index was always 1/3 through the chromosome and the other was always 2/3 through the chromosome. In this picture on the slide, you can see these are the parent chromosomes on the left, and there's 2 points where they're split, and this middle part is switched, and that is how the offspring chromosomes are produced. Lastly, for the genetic algorithm is to incorporate mutation into the mix. I used a probabilistic bitwise mutation, and with this type of mutation, for each character in the binary string, there is a 15% chance, which was chosen by me, that the character will be swapped. For each swap, an existing 1 becomes a 0 and an existing 0 becomes a 1. I generated a random float in between 0 and 1, and if that number is less than my chosen mutation rate, a mutation will occur. This is done for every character in each chromosome, thus creating a mutated population. The whole process I just described is ran for 500 generations, and then the binary string with the best fitness score is extracted and separated into its two subsets. And that shows how the set of numbers were partitioned and the difference between their sums. After that whole process, the wisdom of crowds part of the code begins to execute. And wisdom of crowds refers to the finding that the aggregate of a set of proposed solutions from a group of individuals performs better than the majority of individual solutions themselves. This approach takes all the fittest individuals produced by the genetic algorithm and aggregates them in hopes of producing a superior solution. For the partitioning problem, the way I incorporated the wisdom of crowds was by looping through the genetic algorithm a chosen amount of times, and within the loops, each subset from the resulting fittest solution is stored in a list. So when the loop is finished executing, there is a list that contains every subset from all the genetic algorithm solutions. After this, I created a set of nested for loops that compared every subset from every solution to every other subset and all the other solutions. Then if a certain subset was found in majority of the solutions, it would automatically become the final solution, because if two common subsets make up majority of the solutions produced by the genetic algorithm, then they will be the only ones in the list. However, this use of wisdom of crowds was not very effective. But next, I'm going to give you a demonstration of the results of my code so you can see what happens after it's finished executing. As you can see here at the top, it shows the set of numbers that was produced. This was hard-coded in just for this particular example. As you can see, it loops through the genetic algorithm 10 times. Each time the initial best sum discrepancy between the two subsets is produced. Then after the genetic algorithm has been ran, the final sum discrepancy is shown. Under that, you can see that it shows the chromosome that was produced, and they correspond to the numbers in the subset, and they're split. And it shows under that it shows their split. And then if you come down, when you look here at the bottom, this is where the wisdom of crowds part is. It shows the common sets that were produced in majority of the solutions, and then it tells you what the final partition is and the final sum discrepancy. And this is how the code is ran for all subsets. And then these here are the results of several tests that I ran. So if you look at these two tables, you can see the results of me doing tests on multiple data sets. I did a couple with sets of numbers I knew could produce equivalent subsets, and the last three tests were with randomly generated numbers between certain values. With these tests, the genetic algorithm was looped through 10 times each, and the difference with the table on the left and the one on the right is the program ran through 800 generations instead of 500 generations for the table on the right. I was able to generate good solutions using my algorithm for data sets with less numbers. I was often able to find equivalent subsets using the genetic algorithm, as you can see looking at the tables. And the ones where I didn't, I'm assuming it wasn't possible with the set of numbers that were randomly generated to get equivalent subsets. But as I thought would happen, the wisdom of crowds part of the program wasn't very effective. As you can see from my results on the last slide, when I run my code with a small data set, the wisdom of crowds has a high chance of working. But with larger data sets, no subsets matched a majority of the genetic algorithm solutions, so it's pretty ineffective. And it just ends up using a greedy algorithm I put in the program that isn't optimal for partitioning. The method of this greedy algorithm is just to take the largest number from the original set and place it in one of the two subsets. Then the largest remaining number is then placed into the subset that has the smaller total sum. This process continues until all the numbers have been assigned to a subset. Here's an example of how this heuristic works. This heuristic is better for keeping the sum discrepancy down rather than actually trying to find two equivalent subsets. As you can see, the final sum discrepancy that this algorithm would have came up with is a sum discrepancy of 4, whereas in the code that I showed, the genetic algorithm with the wisdom of crowds was able to come up with a sum discrepancy of 0. The higher the amount of numbers used in partitioning, the more sporadic the final results were. I thought that increasing the number of generations would result in better solutions, but I was mistaken. The results from the runs with 500 generations performed significantly better on average, if you look at that column in the table. Although randomness plays a huge part in the algorithm, I thought that the more generations that were produced in the solutions would progressively get the solutions would progressively get better, but that didn't happen. There are many factors that may have been able to change how well the algorithm performed, but these were the only ones that I chose to test. On this slide, you can see the graphs that display the progression of the genetic algorithm for a couple run-throughs. These particularly are from the data set with the numbers 1, 2, 3, 4, 5, and 7. As you can see, over the genetic algorithm's lifetime, it returns a subset equivalent to 0 several times, but I don't always get the best result, as shown by the graph on the right, where it ended at 6. This is where the wisdom of crowds would be useful, because if the majority of genetic algorithm attempts produced good results, then the wisdom of crowds could use that to produce the best result all the time. But the genetic algorithm gives such a diverse array of results that aren't always the best, so unfortunately my implementation of the wisdom of crowds doesn't work well enough. As I said earlier though, this algorithm can definitely be improved by doing more tests to see how things like increasing or decreasing the mutation rate affect the results. Also, the increasing or decreasing of the number of elite partitions could change things as well. And if changing those things doesn't work, there's always the option of trying out different combinations of crossovers and mutations to see if some other combination produces better results. There could also be a better way of implementing the wisdom of crowds approach than the way I chose to do it. The end result of these improvements should definitely be to find a way to produce better solutions on larger data sets, because overall my code works well on small data sets, but when they get larger, it's not the whole program using wisdom of crowds isn't as effective. And the genetic algorithm can produce um, different kind of results. Sometimes they'll be good, and sometimes they'll be bad. But that is all the information I have to present. I hope you enjoyed this presentation, and thank you for watching.